Good morning to everyone. Uh, Today my discussion is on orthogonal frequency driven multiplexing, that is OFDM. We'll try to understand today that how OFDM signal converts a frequency selective channel to a flat fading channel. Thereafter, we'll try to understand the mapping of time domain data on frequency domain and its conversion to its time domain sample using IFFT. We will take some examples to understand the frequency domain transmission. First, let us start with a single carrier system where that allocated bandwidth, you can see my cursor, total bandwidth is available 10 megahertz. One carrier is placed at the mid of this band. So if you look at what would be the symbol time, that is Ts is equal to 1 by B, that is 0.1 microsecond. Typically delay spread is what that when there is a multipath components, the time difference between the first and the last multipath multipath delay basically is called, the difference is called delay spread. Typically it is 2 to 3 microsecond. Then you can see from the observations that Ts is less than Td. If Ts is less than Td, then it leads to an interference that is called intersymbol interference, ISI. Then what could be done? Instead of placing a single carrier, if we place a multiple carrier, so then what would happen? So 10 megahertz is there. Then if we place a number of carriers, so there will be, each carrier is allocated basically B by n sub that megahertz bands to each sub carrier. Let us take an example where the same problem I will taken with a n, that is 1000 sub carriers. So the bandwidth for each sub band, each sub carrier allocated to B by n, that is 10 kilohertz. So basically the symbol time will be 0.1 millisecond, which is greater than the Td. So in that case we can find if it avoids intersymbol interference. So that's what it is an advantageous if we use a multiple sub carriers to encounter the delay spread, which can affect the delay spread, basically can affect the intersymbol interference. So that's what the multi-carrier modulations, if we use, we can avoid this delay, that ISI. So OFDM means one kind of multi-carrier modulation. Now let us take a channel fading nature, where you can see figure 1. It's a that red dotted line is basically there is no fading in the channel, and the blue that line you can find there's a rally fading. So it's a where if you see here is a deep fade, there is a fading is there, but these lines are deep faded lines, so that gain of the channel is very low. If we look at the figure 2, how we can understand the frequency selective and flat fading. If you look at figure 2, where this blue line is basically the channel response. This is the channel response. Okay, where you can find that first portion there is a zigzag motion is there, up and down. Thereafter the channel is flat. Is this f0 that frequency, this is the amount of frequency for which the channel remains flat. This is basically during this time the each that gain of the channel remain constant. That means each component of each sample of the signal will face same gain. When it passes this channel, it will face same gain. So this is called a coherence bandwidth. If that red line is basically red dotted line, this is the signal, basically signal bandwidth. If we compare these two, so that signal bandwidth is greater than this coherence bandwidth. And if we look at here, these portions, there the signal that channel response is fluctuating. It's not continuous, constant. So that's what the signal will face frequency selective fading. But if somehow if I want to remove this frequency selective, what could be done? Go to the figure 3. We have to reduce the bandwidth with using some technique. If we can place the signal bandwidth here, you can see there is no fluctuation, so the transmitted signal will face flat fading, which is not harmful. Now come to that OFDM transmission, where first we do the channel coding, then serial to parallel conversion, then modulation take place. It may be a PS4, BPSK, QPSK, 8 PSK, 16 QAM, anyone. Thereafter we used to do the IFFT operation. Then we add CP, then we CP, then transmit. Now when you do that, say first if we just will take this from a single carrier system first. Let us consider this frequency. Y-axis is frequency, x-axis is time, where that total bandwidth W that you can remember that I consider for 10 megahertz. I'm talking about this W. Basically here W it is mentioned, here W it is mentioned, and that F0 is coherence bandwidth. This one is coherence bandwidth. Okay, this TS is the basically symbol period. TS is the symbol period, and this entire duration from here to here is the delay space sigma, RMS delay space sigma S. This happens due to the multiple of the channels. Now what is the problem? This one is converted into the frequency domain. If we see, so this signal will face frequency selective fading. How we can say, when we take the next sample, the sample of the previous section, that is this dotted line, will interfere with the next frame. So this is called frequency selective fading. Okay, this how we can be removed. Okay, before going to the the removal of that, just some that what is W. W is equal to 1 by TS. So and here it is mentioned TS less than sigma tau. W is the signal bandwidth, F0 coherence bandwidth, RMS delay spread, TS is the symbol time of signal time of symbol time. Now how it can be removed? The way is to slice the available total W band into n number of bands. So obviously obviously this, if I make a slice, small slice, so the delay become W by n. Okay, so obviously since it is the bandwidth is initially the bandwidth is total bandwidth is W, and W is into TS, that W is equal to, so TS is equal to 1 by W. Okay, now see, since the bandwidth is reduced, so obviously the time that TS which was initially here, TS initially here, since the bandwidth is reduces, so basically the time will increase, so it will move, it may be greater than this sigma tau is. We have to select that DL in such a way that it should be greater than or equals to that sigma is the RMS delay spread. So if we slice this available total bandwidth into n number of subbands, and at each subband we will place one subcarrier. So here I will place first subcarrier, second subcarrier, then nth subcarrier. So W delay is equal to now that is W by n, and TS is equal to 1 by delay. That means that this time interval will be increased by n times. Okay, so now you can see since the TS is greater than sigma S, so there will be no inter-symbol interference. So you can, that is reflected in this figure. So that is basically, this is the basically delay. You can see here. Okay, this is the coherence bandwidth. Now my transmission bandwidth is less than the coherence bandwidth, so it will not face any this channel gain fluctuations. So signal will not be affected too much. Means that the signal will the channel becomes flat for this transmission. So So that's what we can see. WebDM converts a frequency selective fading to a flat fading channel. Now we try to understand the same the time and frequency domain. This side is basically, this x-axis is basically frequency and this y-axis is basically time. For an example, say an WebDM frame, we want to, this is an WebDM frame, this is an WebDM frame, is divided into say 64 subbands. So basically we will place 64 subcarriers here, 64 subcarriers here. Okay, 1 2 3 4 up to 64, one OFDM symbol, and each carrier will carry one message points that depends on, that message point depends on basically modulation technique. If it's a PPSK modulation, each subcarrier will carry 1 bit. If it is a QPSK modulation, each subcarrier will carry 2 bits. So from this point, from this end, there are 4 symbols are there. See, for this, if I take this orange one, during this time, how many samples are there? 60. For say, let us consider BPSK signal. So 64 subcarriers are there. So each subcarrier will carry 64 bits. So sir, 1 bits. So since there are 64 subcarriers, so during this time 64 bits will be transmitted. After that, that's a CP. This one is CP. Second symbol, the same 64 bit, then 64 bit here, 64 bit this point, this in terms of time, then CP. Let us try to understand this through some examples. Determinants of number of bits are carried by 4 OFDM frames in a BPSK modulated system with n is equal to 64 subcarriers. So since there are 64 subcarriers and BPSK modulations, so each BPSK modulation means each symbol will be represented by 1 bit. So 64 subcarriers will carry the 64 bits. Okay, since there are 4 symbols, so if I go back to this previous one, so if there are, this is 64, this is also 64, this is also 64, this is so 4 into 64, that means 256 bits will be transmitted for these 4 OFDM frames. Similarly, if I extend the problem with for QPSK modulations, then each subcarrier will carry 2 bits. Let's go back to this figure, means here 2 bits, here 2 bits, here 2 bits, here. So 64 into 2, that is 120 bits. Means this 120 bits will be accommodated here. This is the time domain. And then CP according to that it may be 10% of the total OFDM frame, depends on what would be the length of the CP, that is depends on the channel delay spread. Okay, so if we see this problem, so 64 into 2, sorry, then 64 into 120 bits, since there are 4 OFDM frames, 4 into 120, 512 bits will be transmitted for 4 OFDM frames. If we extend the same problem with 16 COM, then each subcarrier will carry 4 bits, that is 64 into 4, 256, and 4 OFDM frame, means each OFDM frame will carry 256 bits, and 4 OFDM frame means 4 into 256, that is 1024 bits. So is very so what you have to understand that frequency and time domain interactions. Basically, frequency domain, what we are doing, we are placing, when we are go back to there, basically what we are doing, we are placing the subcarriers at the frequency bands, then on the top of that we are placing the time domain data, then we do the IFFT and converts this time domain data, that is frequency domain data, into time domain data. That's what it is. That's what that I50 is used here. What are the steps? Basically, if we try to understand frequency domain, the data symbols are assigned to any subcarrier in the frequency domain. These symbols are placed at a specific frequency bins, ensuring orthogonality. Means that carriers should be orthogonal to each other. Then we will do the IFFT. The IFFT take these frequency domain samples and convert them into a time domain waveform. The IFFT operation is given or is belong to U. So here is basically this XK is basically this BPSK. This is the data. This is the time domain data. We'll take this example. We'll try to understand. Then parallel to serial, then add CP, then digital to another conversion and transmission take place. Now, why is this frequency to time domain conversion? Because in OFDM data symbol, QPSK, PSK data are mapped onto subcarriers in the frequency domain. That's what is called a frequency to time domain conversion. Each subcarrier represented are different frequency components. The signal is represented a discrete frequency samples. Then I50 operation is done. Then the I50 takes this frequency domain symbol. Basically, once we are placing this BPSK or QPSK data on the subcarrier, basically they become frequency domain signals. Once we do the I50 operations, they convert it into time domain signals, and it combines this I50 combines all subcarrier into a single time domain. Means once we do the I50, then it will generate the time domain data, that is XN. That XN will generate. This is the time domain data. Now let us take an example to understand this OFDM transmission. It is a BPSK, either it is a +1 or -1, 4 subcarriers X0, X1, X2, X3. We will place on the top of the subcarriers either 1 or -1. So that's what if we do the I50. So if we X0 is basically X0 is X0 1 by 4, X0, X1, X2, X3 and X1. So basically all these time domain samples are combination of this X0, X1, frequency domain samples. So that's what XKR modulated. This XKR basically BPSK modulated symbols. Keep in mind. Examples. We are taking examples. Let us assume X is equal to 1, -1, +1, -1. Basically, we are placing this time domain data on the subcarrier. So this XK, the X is basically represented as +1, -1, +1, -1. Now if I do the I50, then we'll find that after I50 it becomes 0. It's a complex signal. It becomes a complex signal. It looks like this. We have taken an example. So we want to transmit 1, -1, 1, 1. It is the frequency domain BPSK signal. It looks like this. When it is converted to time domain signal, so it would have time real and imaginary part. It's a complex signal, and it will look this is the time domain signal after OFDM modulation, I50 operation. That is okay. Now if we repeat the same thing, instead of BPSK modulation, if we use the QPSK modulation, then our that XK maybe I1 plus G or 1 minus G or -1 plus G or -1 minus G. So based on that, we'll try. If we find that what would be the time domain samples, so X0, X1, X2, X3, we can find that the result is basically 0, 0, 0. Okay. So what is this? What are the summary? That I50 converts frequency domain QPSK symbol into time domain samples. The time domain samples are complex payload containing real and imaginary parts. Orthogonality is maintained among subscribers. Hybrid prefix is used to prevent inter-symbol interference. Thank you.